So MIDI stands for Musical Instrument Digital Interface. So what is that? What is Musical Instrument Digital Interface? It's a digital communications language and compatibility specification that allows multiple hardware and software instruments, performance controllers, computers, and other devices to communicate with one another over a connected network. MIDI is a language, okay? So it's a way that hardware and software devices communicate with one another. It is a way that we can set up a whole network of all of these hardware and software devices so that they work together, so that they can create one larger controllable network of many different devices. It translates performance and control events into digital messages. So these events are something that you do. So an event could be pressing down a piano key. An event could be twisting a knob. An event could be depressing a foot pedal. An event could be moving a modulation wheel on a keyboard. So all of these are events. They're things that happen in time, and all of these events typically are enacted by a human being. So it's translating. So let's think back to our discussion of the difference between analog and digital information. Analog is continuous. Digital is discrete. MIDI is a digital language. It's translating continuous events into discrete messages. So the continuous event would be you pressing down a key on the piano. That needs to be translated into a digital message that's going to be sent to this whole network that could be a computer, another keyboard, anything that can understand MIDI as a language. So it is also an interface. So what does that mean? Interface refers to the actual data communications link and software hardware systems within the connected MIDI network. Through the use of MIDI, it is possible for all electronic instruments and devices within a network to be addressed through the transmission of real-time performance control messages through a single MIDI cable. So, in other words, we are able to plug all of these different instruments into one another, and from one control room, one cockpit, we could really think of it as, wherever you are in control of this network of digital electronic musical instruments. And through these cables, they are able to all be connected to you so that you can control multiple keyboards all at the same time. You can control all of these devices through your 10 fingers and 2 feet all at the same time. So that's the interface aspect of it. So, in other words, MIDI, this is what MIDI is not. It does not communicate audio. MIDI does not create sounds. MIDI is not electronic keyboards. Of course, MIDI relies on audio, the creation of sounds, and electronic keyboards in order to be meaningful. But MIDI itself is not any of these things. MIDI is a language, is a programming language. So we associate this programming language with particular sounds, right? That might be a particular keyboard or a particular drum machine or whatever. But those keyboards and those drum machines are the digital instrument. They're the instruments, the electronic instruments that are being controlled or being talked to through MIDI. MIDI is the way that they talk to one another, not the sounds themselves. And this is important to remember as we go forward, that really when you're manipulating MIDI, you are using a type of programming language. This is a programming language that we're learning. Okay, so it's a language. Then what does it communicate? Don't worry. As we go forward, this all is going to make a lot more sense when we start messing with it and I start demonstrating some things. But this is just sort of an overview of the different fundamental parameters or fundamental elements of this language. Okay, so the components of this language are note numbers, 127 of them. Now, you might be thinking, why 127? I mean, there are only 88 keys on a keyboard. I'll get more into that later. But they decided on 127 note numbers. These note numbers are paired with on or off messages. Okay, so this sounds familiar, right? All digital is ones and zeros. All digital information is really just on and off messages. So we have note numbers that are paired with on and off messages. We also have control values, which also are scaled from 0 to 127. So control values would be like the knobs on the electronic keyboard that you have. So as you turn the volume up, you are going from all the way to the left to all the way to the right. That is scaled in MIDI language to values between 0 and 127. MIDI relies on a time code, which is really just, in other words, a clock that synchronizes all the instruments so that they are playing at the same time. It uses a logic of master-slave relations. So you're going to have one MIDI instrument that is where you, as the pilot of the musical journey, are using that MIDI instrument to control others. So that is the master that is sending out control messages through a cable to other MIDI devices, or I should say to other electronic devices, computers, instruments, etc. And they are receiving that, so they are receiving it from like the master keyboard. And it also has velocity information, which is how fast a key is pushed down. And we'll get back to that at the very end of this lecture. Why velocity? But these are the elements of MIDI. So it is a language, and it uses each of these types of information to, and they all sort of combine into the control messages that create music. Okay, so let's dig into the history of MIDI and this will help us to understand how these instruments developed and why the language is constructed the way that it is. So MIDI, again, as a language, is invented in 1981 by this guy, Dave Smith. So, again, he invents this language that is about note numbers, 0 to 127, controls, all of that. So, and we're looking at him standing behind a synthesizer, and you can see already, this synthesizer has, it looks like it's probably a 66-key synthesizer, and it has all those knobs and buttons on top. So Dave Smith was already working with synthesizers. There were many different companies who were developing synthesizers with new, based on the new digital computer technology that was emerging at the time. So you have all these different companies from different countries, all developing the same sort, developing within the same realm of electronic digital musical instruments. And musicians started to want to get these different keyboards to communicate with one another. So they wanted to have these. So if you bought this particular keyboard and then the one that's behind him, or the several that are behind him, he wanted to figure out, well, how can I get all of these keyboards to play with one another? And so there was this desire to do this. Part of this desire, or this push towards getting all of these instruments that are built by different companies to talk to one another, came from this man, Ikutaro Kakahashi. So Ikutaro Kakahashi was the founder of Roland. I don't know if that is familiar to all of you, but Roland was one of the first digital synthesizer manufacturers. And Ikutaro Kakahashi was the designer and developer of some of the more important digital synthesizers in popular music. So if you go back through all of the Roland contributions to musical instruments in the 1980s, I mean, it's really amazing how much the instruments that he designed influenced popular music. So not only was he inventing instruments, but he also had an interest in finding a way that instruments from different manufacturers could communicate with one another. Okay, so here is young Ikutaro Kakahashi in his really dapper lab coat. I love that he's in a lab coat, and he's working with an earlier electric piano. This is probably taken before he founded the Roland Corporation. So Roland is a really important company. Ikutaro Kakahashi is a really important figure in the development of not just these electronic digital instruments, but MIDI as a language. So Kakahashi gets in touch with Dave Smith and says that he wants there to be a language that allows instruments from multiple manufacturers to communicate with one another. Not everyone in the industry was interested in this. In fact, instrument makers in America were actually very resistant to this idea. They had already been developing proprietary communications languages that really were about making sure that their instruments could speak to other instruments that they made, but they wanted it to be proprietary. Kakahashi is fighting against this, and he gets Dave Smith to develop MIDI as the language that can let all electronic digital musical instruments communicate with one another. So this happens in 1981. And this really revolutionizes popular music and art music. This becomes a really one of the more important developments in music technology in the second half of the 20th century. So, but before we get there, before we get to 1981, when Dave Smith invents MIDI as the language, as I mentioned, there are all sorts of electronic synthesizers that are being developed. So we can think of 1950 to 1980 as this really sort of heyday of the development of new electronic synthesizers. So I've got 4 examples up here on this slide, and I'm going to start in the top left corner and go around clockwise. So here we see a Moog synthesizer, M-O-O-G, that some of you might have heard of. So this is an electronic synthesizer that uses electrical currents to modulate one another. And basically you have a keyboard that is controlling the on and off messages to these different electrical oscillators that you can turn knobs on and plug into one another. This is not a digital instrument. This is an electronic instrument. It is analog. To moving clockwise, we've got a Buchla synthesizer, similar to the Moog. And what's nice about this photo is you can see that both of these synthesizers, the part of how they worked was you had these cables and you could plug different electronic oscillators into one another, and so that they would affect one another, modulate one another. Again, you have the traditional piano keyboard that is controlling the different electronic oscillators, and then you have all these knobs. And again, this is an analog instrument. It is not digital yet. Moving around again, clockwise, we see Harold Bode. And I like this photo because you get to really see these earlier musical laboratories and how they were all sort of these interconnected spaceships almost. So here he is working on one of his early synthesizers. Again, you can see all of the cables in the background, and these are different oscillators plugged into one another, affecting one another. And then moving around to the last photo, again, this is in the bottom left. You see Peter Zeithaif, and here he is sitting next to one of his early synthesizers. This one is interesting because it does not have a traditional piano keyboard. So this is all about playing knobs. And so we can think of this as, again, it's analog, but it's very similar to the different sort of control devices that would be used for MIDI later, i.e. knobs that you rotate to change different values. So these are all examples of electric synthesizers or electronic synthesizers that were being developed in this time. They are not digital. Leading up to 1980, so in the late 70s, different companies start to develop digital synthesizers. So Yamaha, Roland, all of these companies are developing these digital synthesizers that are digitally synthesizing sound, not with electronic oscillators, but with bits and bytes. And this is really where people start to understand. Once all of these synthesizers go digital, people like Dave Smith and Ikutaro Kakahashi can see the potential in being able to connect these synthesizers. So when we're looking at these pictures here, we have these literal connections that are happening with these cables, right? If we look at the Buchla in the top right and the Bode synthesizer in the bottom right, you have these physical connections that are happening through these cables. And with digital, people like Dave Smith and Ikutaro Kakahashi are starting to say, oh, wow, we can connect everything in our studio together and control everything at the same time. So this is really what is the impetus, the drive that's happening behind MIDI in the early years. It's coming out of the development of this, this huge amount of creative work and technological innovation that is happening post World War II in developing these new synthesizers. Now, before that, before the rise of the electronic synthesizer from 1950 to 1980, we have some even earlier examples of electronic synthesizers. So, over on the left, we see the cover of a popular electronics magazine from 1955. The theremin. I don't know if any of you are familiar with the theremin. You are probably familiar with the sound. So think of Good Vibrations by the Beach Boys. And that sound that goes, woo, that sound is a theremin. It is, and the way that you play a theremin is it senses through magnetic field how close you are to a rod. So as you can see in this photo from Popular Electronics, this drawing of this man, the man is playing the theremin with one hand he is controlling the change in pitch, and with the other hand, he is controlling the change in volume. Leon Theremin, the Russian inventor, developed this in, I believe, 1915, somewhere around World War I. He developed this instrument. It again is analog. It is continuous control. But what you are able to do is convert the distance you are from a metal rod into changes in pitch and changes in volume. So that sound, that theremin sound that we associate usually with like early science fiction or with the Beach Boys song, comes from this instrument. And we can think of the scaling of 0 to 127 as related to this, coming out of this sort of conceptualization. Over on the right, we see the teleharmonium, which is another early electronic synthesizer that was using little. This is like the very beginning of using little electronic oscillators to create sound. And that's early 20th century as well. So these are instruments that were being developed in the early 20th century and predecessors to later electronic synthesizers. At the very turn of the century, we have a non-electronic synthesizer. So the player piano. The player piano. I don't know how many of you are familiar with this, but it's like the piano that you've seen this in movies or shows, where it's the piano that can play by itself. So all of the piano keys have a mechanism that can be automated, and so the piano can just sort of play by itself. And this was invented in 1900, and the very first player pianos were not electronic, but they were pneumatic. In other words, they were controlled, or the energy that was driving them was steam, was gas. Later ones became electronic. So this is an example of automation, and this is something we're familiar with by drawing automation curves into Studio One. But it is also obviously an important element of MIDI, in the sense that you can send control messages through a network. And here we've got automation, and there are control messages that control this piano, control the mechanism of when the keys are pushed down. So how does this mechanism work in the player piano? Here is a closer look. So I'm going to go back to the previous slide. You can see above the keyboard, where you might be looking at the sheet music, there is this opening into the piano. And what that is a piano roll. So here is the mechanism removed from the player piano. And what you see is a scroll there, and so whatever is driving the player piano, whether it's electricity or steam, that's going to rotate these gears that you see on the right, and the gears rotate the scroll. And as the scroll moves, that moves in time. So you can think of the scroll rotating as similar to when you're looking at Studio One, and your time is moving from left to right. So here, the scroll is moving from bottom to top. So let's take a close. So what you see there in the scroll, it's been perforated. So if you look on the right of the scroll, you see these perforations. That's a series of dots that you can think of as the grid. To the left of that, you see these longer perforations, and that correlates to if we're looking from right to left on this scroll, that would be from the bottom of the keyboard to the top. I might have it reversed. Maybe it's from the top to the bottom. And as you're looking from top to bottom on the scroll, that is time, right? So when you see these longer perforations in that scroll, those are longer notes. When you see shorter perforations, those are shorter notes. When you see these perforations as separated from right to left, that is from low to high, as far as like correlations to the piano keyboard. Now, this idea, here's another picture here. You can see a piano roll, a traditional or a player piano roll on top. And when we talk about MIDI in Studio One, we still use the term piano roll. So you can see the piano roll in digital form on the bottom, and that's a screenshot from Studio One. So, and now look, you can see that in the piano roll, you can see over to, so if you look at that, the digital version, the Studio One version, if you look over to the left of that shot, you can see a representation of the piano keyboard. Then you can see these perforations, quote unquote, to the right. So you can see how there are notes that last for a certain amount of time from left to right, that from top to bottom that correlate with different keys. And so as time moves from left to right, you could think of the piano roll in Studio One as working exactly like the piano roll in a player piano. In other words, the piano roll is sending out messages that are, this note starts now, this note stops now. So it's a series of on and off messages, whether we're looking at an old school player piano, or whether we're looking at MIDI and how we're going to be dealing with it in this class. It is really the same thing. And it's pretty interesting to see how this technology that was developed in 1900 ends up being a really fundamental element of MIDI language that was developed 80 years later. So this is, so we really are looking at, we've looked at the 20th century as the development of the electronic synthesizer and how that relates to MIDI. Just to sort of recap here, MIDI as a language really kind of emerges in many ways out of the technology of the player piano, where you have a scroll, a piano roll, that communicates a sequence of on and off messages to different note numbers. And we also looked at how the 20th century, we see a proliferation of synthesizers being invented and a subsequent need to find a way to get all of those synthesizers to communicate with one another. And this leads to the creation of the musical instrument digital interface. This interface is a way that all of these things can communicate through one single piano roll. Now, so we've really been talking about electronic synthesizers and, as I mentioned, pneumatic synthesizers. But there are earlier examples of synthesizers. So what we see here, this is a mosaic, fourth century mosaic. So this is like 300 current era, or AD. And this is a mosaic, and you see a group of female musicians. On that table there, this woman is playing a collection of metal bowls. So they're I don't know if you've ever heard a temple bowl before, but that's what she's doing. There are these metal bowls that resonate, and you sort of drag a rod around the edge, and it kind of lets out this ringing bell sound. And then you've got a harp behind her. So there's a harp there. But then over to the left, you have a organ. It's a pipe organ. So the pipe organ existed in 300 AD. It was invented all the way back in ancient Greece in 300 BCE. So the way that the premise, how a pipe organ works, is you have some sort of mechanism that pushes air through a pipe. The pipe is a certain length, and the length of the pipe correlates to a specific frequency. Okay? So a shorter pipe is going to create a higher sound. And you can mathematically figure out what that sound would be. And you can figure this out based on all of the math that we learned in the first half of the semester. So, and how do you figure that out? Well, if you can figure out the wavelength you could figure out the frequency based on the length of the tube. So the length of the tube is going to correlate to specific hertz, and so you can tune an organ just like you can tune anything else based on the length of the pipe. So here we have an automated instrument, right? So you can think of a pipe organ as somebody came up with the idea like, oh, look, we have these flutes. So everyone's playing flutes. So similar to how Ikutaro Kakahashi and Dave Smith were thinking like, well, what if we were able to control all of these digital instruments at the same time from the same place? People in the 3rd century BC were thinking the same thing. How could we control a whole bunch of flutes at the same time and in the same place? So instead of just having one flute that is controlled by one set of lungs, what if we had a mechanism that pushed air through a whole bunch of flutes? So it's the same sort of thinking, and this is the development of the earliest organs, and they all worked this way. There was a bellows, or like a sack of air that could be pushed and then controlled, and you sort of channel the air through whatever pipe you want to channel it through. So this machine, this organ, again, a pipe organ is a machine, dates all the way back to 300 BCE. Of course, we are more familiar with pipe organs in relation to the Christian church, I would assume. Okay, so again, we've got a pipe organ is an automated musical machine where you can control multiple instruments from one place. So it's an interface. We could really think of this as an analog interface. So all of those pipes that you see are controlled by one keyboard. So in that sense, it's an interface. Why is it that how can I call this a synthesizer? So I've convinced you that really this is an interface, right? So in what way is this also a synthesizer? So here is another viewpoint of the organ. Here is what it looks like from the perspective of the performer. So you have these multiple keyboards, right? And then to the right or to the left, you have all of these what are called stops. They're buttons, really. But instead of depressing them, you pull them out. Now, when you pull out a stop, basically what that does is it cuts off the pipes at a certain point. And what that does is it changes the sound of the pipe. You can make it more flute-like or more violin-like. So all of these stops will even have those names, like the flute stop, the flute register, et cetera, et cetera. So by pulling out these stops and changing the way that the air is flowing through the pipe, people were able to figure out how to synthesize other sounds. So the desire in creating this interface of this network of stops that change the way the air is flowing through the pipe was a way to synthesize non-pipe sounds. So to make it more flute-like, but also make it more like string-like. So when you hear a really elaborate and really well-designed church organ, listen for how the sound of the organ is able to change, to become more bassy, to become more trebly, to become more airy, to become more woody. All of these changes in the nature of the sound are done by pulling out these buttons that change the way that the air is flowing through the pipes. And this is why I'm saying that really this is the first synthesizer, because it is synthesizing another sound. It is creating a mechanism that is trying to reproduce or replicate or mimic another sound through a machine. So we can think of the pipe organ as the first synthesizer, both in the sense that it is mechanically operated, that it is that there is a mechanism that distributes control to a whole bunch of different places from one sort of cockpit, but also in the sense that it was designed to mimic the sounds of other instruments. Okay, so now let's think about both the player piano and the pipe organ. Both of them use piano keys to communicate the messages, to distribute the control across the musical instrument from the performer. Now, what that is communicating, right, if we're going to now move over to digital information, what that is communicating is a different types of information. So when I push down a piano key, really I can send the things that I can measure. If I am measuring or if I'm measuring a set of piano keys, the types of information I can get are which key is down, which key is up. So in other words, on, off. I could also get a sense of how far the key is pushed down, but really the mechanisms on these electronic keyboards. So if you were to have a mechanism that could really just measure like how far the key had been pushed down, it would be very fragile. However, they were able to develop a much more strong, sturdy technology that could measure how fast the key went down. So the speed of the key going down, of course, correlates to how loud the note is on a piano. Now, if you've ever played a pipe organ, you'll know that if you press the key down slowly, or if you put a lot of pressure on the key or very little pressure on the key, it does not change the volume of the sound. The way that you change the volume of the sound is how much air is going through the pipe, right? And you control that with which stop you're pulling out. So these buttons on the left or the right. So that's how you control how loud it is, because the mechanism of the pipe organ does not care about how hard you push down on the piano key. But a piano does, because a piano is a hammer, right? It's a hammer that's striking a string inside of the piano. So if I push down really hard on a piano key, it's going to strike that string really hard. If I press down very soft, it's going to strike that string very softly. So that it doesn't work that way with an organ. So if I want the organ to be loud, I need to push more air through, and the mechanism that allows me to push more air through is opening more stops. What MIDI allows people to do is to make the control coming from the piano keyboard much more like a piano. In other words, you can send more information. So when we're looking at a church organ, the information that's coming from the piano keyboard is only on and off messages. It's only play this C sharp at this time, stop playing it. In other words, let air through this pipe, stop letting air through this pipe. That's the only set of information that can come from the piano keyboard in an organ, on and off. With MIDI, you're able to both communicate on and off and how fast the key is being depressed. And you can, of course, convert the speed at which the key is pushed down into loudness. So here we're looking at the envelope of any sound, and this is familiar from how we discussed this in the first half of the semester, ADSR, attack, decay, sustain, release. This is how we describe the envelope of any sound. Now, this can be correlated to these three messages. So the three messages, it's three messages, which is on, speed of how fast the key went down, so on, speed, and off. Those are the three messages. So on, velocity, and off. And that can be mapped onto the envelope of the sound. So here we see our envelope, our ADSR, as correlated with the information coming from the keyboard. So at the moment in time that I push down the key, that triggers this shape in time of the attack and the decay. And when I release the key, that tells the note to then decay the sound, to release, so to trail off. The speed at which I push down the key tells the electronic instrument how loud it should be, what the amplitude should be.